In this problem given f of x is equal to greatest integer of x for x belongs to pi comma 9. We are going to verify Rolle's theorem and converse of Rolle's theorem. So first we are going to check the continuity at this point pi. So left hand limit, I am going to check the left hand limit. Put x is equal to pi minus h. As x tends to pi, h becomes 0. So limit x tends to pi, f of x is equal to limit x tends to 0. This x is substitute pi minus x here, greatest integer of pi minus x. What is pi minus x? So some values less than pi, like 4.99, etc. So pi minus h is nothing but greatest integer of 4.999, that is equal to 4. So now RHL is put x is equal to pi plus h. So as x tends to pi, limit pi f of x is equal to limit h tends to 0, greatest integer of pi plus h. What is pi plus h? Pi plus h is nothing but some values like 5.001, etc. So this becomes 5.01 becomes greater pi. So see, LHL is 4 and RHL is pi. LHL not equal to RHL. Therefore, f of x is not continuous in interval pi comma 9. Since it is not continuous, it is not differentiable. Also, given intervals are 5 and 9. So f of x is equal to greatest integer of x. So f of 5 is equal to greatest integer of 5 is 5. Also f of 9 is greatest integer of 9 is 9. So f of 5 is not equal to f of 9. So all the three conditions are not satisfied. F of x is not continuous, f of x is not differentiable, and f of a is not equal to f of b. So Rolle's theorem is not applicable. So now let us check the converse of Rolle's theorem. So for converse of Rolle's theorem, I am taking a non-integral point 6.7 in between 5 and 9. Given intervals is 5 and 9, I am taking one point 6.7. So f of x is equal to greatest integer of 6.7. 6.7 belongs to 5 comma 9. So now LHL, I am checking the continuity, going to check the continuity. So LHL, put x is equal to 6.7 minus h. As x tends to 6.7, h tends to 0. So limit h tends to 6.7 minus f of x is equal to limit h tends to 0. Substitute the 6.7 minus h here. It becomes 6.7 minus h is equal to 6, because 6.7 minus h is nothing but some values like 6.66, etc. So greatest integer of 6.666 is 6. RHL, put x is equal to 6.7 plus h. So as x tends to 6.7, h tends to 0. So limit x tends to 6.7, f of x is equal to limit h tends to 0, 6.7 plus h is equal to 6. What is 6.7 plus h? 6.7 plus h is nothing but some values like 6.811. So this becomes greatest integer of 6.811 is nothing but 6. So LHL is also 6, RHL also is 6. So LHL is equal to RHL. Now, therefore f of x is continuous at 6.7. Now let us check the differentiability. I am going to check the differentiability. Now LHD, put x is equal to 6.7 minus h. As x tends to 6.7, then h tends to 0. So limit x tends to 6.7, f of x is equal to limit h tends to 0. We know the differentiability formula. F of a minus x minus f of a by minus h. So f of here 6.7 minus h minus f of 6.7 by minus h. What is 6.7 minus h? I already told 6.7 minus h is equal to 6. So 6 minus here also f of 6.7 is 6 by minus h. So 6 minus 6 is 0 by minus h, that is equal to 0. Now we have to check the RHD. So RHD, put x is equal to 6.7 plus h. As x tends to 6.7, x tends to 0. So limit x tends to 6.7, f of x is equal to limit x tends to 0, f of 6.7 plus h minus f of 6.7 by h. So what is 6.7 plus h? We already saw greatest integer of 6.7 plus h is equal to 6. Also greatest integer of 6.7 is 6 by h. So 6 minus 6, that is 0 by h is equal to 0. So LHD is 0, RHD is also 0, both equal. Therefore f of x is differentiable at x is equal to 6.7. But what is f of I? F of I, greatest integer of I is 5. What is f of 9? Greatest integer of 9 is 9. So f of I is not equal to f of 9. So what is converse of Rolle's theorem? Converse of Rolle's theorem states that if f of x is continuous, f of x is differentiable, and f dash of c exists, then f of a should be equal to f of b. So, but in this problem, f of x is continuous at 6.7, f of x is differentiable at 6.7, and f dash of x exists, but f of 5 is not equal to f of 9. So converse of Rolle's theorem is not true. I hope you understand this problem. Thank you.